Now we try to check whether two given data series come from the same probability distribution. So let us open a new script. You copy paste what is given in the description of the video. So again we are working on the iris data set. So again I'm going to run the iris data set. You select this and you hit the run button. And here now we are going to compare two data series. We will compare petal width of setosa with petal width of species versicolor and see whether these two data series come from the same population. So that is what the command is, t.test, and then instead of one I just have put the second here. So there is nothing much to be done. As you can see, this is setosa and then this is versicolor. So you can just copy paste this from the description of the video, and let us run these two lines. So you select these two lines and you hit the run button, and this is what you get. You get the value of your t statistic. Your degree of freedom is 74.755. P value is given to you as 2.2 e to the power of minus 16. That is means 2.2 times 10 to the power of minus 16. So what does this p value mean? So p value calculates the probability that these two data sets are coming from the same probability distribution. That is this setosa and versicolor, they are coming from the same distribution. So you can see the probability is very low. So that means the alternative hypothesis is true, that is difference in means is not equal to 0. So by default R will set the hypothesis as that the mean is equal, and here you can see the difference in mean is not equal to 0. So the 95% confidence interval gives you minus 1.14 to minus 1.016867. So you see 0 does not even lie in this interval. So since 0 does not lie in this interval, you also reject it. And R will also calculate you mean of x and mean of y, that is two data series. So the setosa has mean of 0.246 and the second one, this versicolor, has a mean of 1.326. So everything is beautiful in this example. We will see another example where we see some kind of a problem. Now I have these two data sets, say my data and your data. So these are two data sets and we want to run a t-test on that to find out whether the mean is the same. That is, do these two data sets come from the same population? So to run this, you just select everything till my data and hit the run button, and you get values. So t statistics is 1.2734, degrees of freedom is this, p value is 0.2. So p value is actually more than 0.05. So the way the statistics work, or the thumb rule is, if the p value is more than 0.05, then you accept the hypothesis. So since it is more than 0.05, you can say that the difference between means is not equal to 0. So the alternate hypothesis is true. So default hypothesis of R was that the mean between the two populations is 0, but here we are saying the alternate hypothesis is true. Now look at the confidence interval. So notice that 95% confidence interval goes from minus 0.3 to 1.5. So 0 lies within this interval. So we should not have rejected the hypothesis to begin with, but we rejected the default hypothesis, and we are saying that the difference in mean is not equal to 0, whereas 0 does lie in the interval here. So here we said difference in means is not equal to 0, and 0 did not lie in the interval here. And here the 0 does this 0 does lie in the interval here. So that is a problem, and that is corresponding to this p value. So the probability is actually 0.2. So the probability that these two means are equal is 0.2. There is, which is not a huge probability. This is like a small probability, and that is the problem. basically the thumb rule is, at least what people try to follow, is that in such cases you should actually reject the alternate hypothesis. You cannot say much about it because your confidence interval contains 0. So this confidence interval contains 0 and your p-value is not very high. P-value is still low, although you have accepted it because p-value is still it's greater than 0.05, and therefore you have accepted the hypothesis, but it is still pretty low. It is just 0.2. So you can see the dichotomy here. It depends upon you what you want to do with such a hypothesis, but I would ideally say that you should say that more data is required so as to make the test more conclusive. So ideally you should just focus on the 95% confidence interval and see that this 0 should not lie in this interval. If the 0 lies in this interval, then you need more data, although your p-values are good enough.